We're going to look at some examples now in section 3.4 involving different rates of change. And our first example looks at the rates of change relating to motion of an object, which we just got a bunch of definitions for. So this problem says we have an object that is moving on a coordinate line such that it has a position given by the function s equals f of t. It's a function of time. That function is 3t minus 4t squared plus t cubed, or if you prefer, you could write that as t cubed minus 4t squared plus 3t, if you want to put the terms in descending order. But that's our function. We're looking at the time interval 0 to 4. So 0 is less than or equal to t is less than or equal to 4. S position is in meters. T time is in seconds. Okay, so we're going to find a couple different things for this, starting with our object's displacement and average velocity for our time interval that we're interested in. So let's start with displacement. And all the definitions are earlier on in this packet here. And our definition for displacement was that we had delta S, because displacement really, remember, is a change in the position of the object. And so that was going to be f of t plus delta t minus f of t in terms of our earlier definition. But remember what those two inputs of time really meant. This is like the ending or finishing time, and this is just the start time right here. So it's the overall idea, it was where does the object end up minus where did it start. So it's like ending time and starting time. So in our case, we could say that that ending time is going to be 4 seconds and our starting time is going to be 0 seconds. If we want a measurement for that delta t, which we will need that eventually, the delta t we're looking at here is just 4 seconds have elapsed. So between our start and our end, that's what we're looking at here. So whichever way you care to look at it, this is going to be f of 4 minus f of 0. That's the overall idea. All right, now we got to calculate those out here. So we're going to use our function f of t here to find f of 4. And I'm going to go ahead and use this terms written in descending order version here, this f of t, just because most of us are used to seeing the terms written in decreasing degree order. So we have 4 cubed minus 4 times 4 squared plus 3 times 4. Okay, there's f of 4 minus f of 0, which if you look at that, plugging in 0 for all of that t's is just going to give us 0. But I'll write it out. 0 cubed minus 4 times 0 squared plus 3 times 0. And now we can really see that that is all just 0. Okay. So here we've got 4 cubed, which is 64, minus another 4 cubed there, minus 64, and plus 12, minus 0. All right, so we end up getting 12. And for all of these problems, remember to put your units on here, because that's a big part of this. So our displacement, notice how that is a change in position. How far has this traveled? We're going to say it has traveled 12 meters because that is our position measurement here. So 12 meters for the displacement. Okay, and then we also want to find the average velocity in this first part here. Average velocity. Okay, and that is our V AVG. All right, V sub average. And definition for that was the distance traveled over the time elapsed. Okay, which conveniently we have just found that distance traveled, delta S, that is our displacement. So we have 12 meters up on top there, and the time elapsed is 4 seconds. All right, which we could just use S to represent seconds there. And so we end up getting 3 meters per second for our average velocity. Now, remember, that's just average. The instantaneous velocity of this object could definitely be changing in our interval, but this is what it averages out to. Okay, next part. We want to find the object's speed and acceleration at the endpoints of the interval. Okay, so notice how they are talking about the endpoints of the interval. So we are going to be finding speed and acceleration at these individual points. So this is going to be referring to instantaneous speed and instantaneous acceleration, since we're focusing on just a single point for each one of those. So our endpoints are going to be t equals 0 seconds and t equals 4 seconds. So we have two different points that we're looking at, but individually. Okay, so we'll look at the endpoint t equals 0, find speed, find acceleration. We'll look at the endpoint t equals 4, find speed, find acceleration. Okay, let's start with speed. Okay, so speed, if you'll recall, is just the absolute value of velocity. It's velocity without the direction component. So speed is going to be absolute value of v of t, okay? Which v of t, again, that's instantaneous velocity that we're looking at there. So that is the derivative of position, ds dt, or f prime of t, if you'd like to look at it that way. Okay, so let's take a derivative of our function here, f of t. Again, I'm going to use that yellow highlighted version, and we can use the power rule on this most definitely. So we'll have 3t squared and then minus 8t plus 3 for that first derivative there. Okay, so we can find the speed at our first endpoint, t equals 0. That would be absolute value of v of 0. So we're taking the absolute value of the velocity at that endpoint. And that would be plugging in 0. You can probably see what it's going to be because the numbers are nice. Okay, the first two terms here drop out. And so we're going to end up with absolute value of 3, which is 3. And our units on this, remember, because we're talking about a speed, it's going to be in meters per second. Okay, just like velocity. Since we're just taking an absolute value of velocity, the units are staying the same. And now let's find our speed at the other endpoints. Plug in t equals 4 instead now. And we're going to have 3 times 16, which would be 48, minus 8 times 4, which is 32, plus 3. And so that'd be the absolute value of 19 for that. And so we'll get 19 meters per second. Okay. Now, having the absolute value on these particular velocities didn't make a huge difference because the velocities inside were positive anyway. But remember that, if those had been negative velocities, finding speed would have stripped out that negative directional component. Okay, so there's speed at the endpoints, and then we were also going to look for acceleration at the endpoints. So let's do that. Acceleration. And in order to get acceleration, remember we're going to have to take another derivative here. A of t is the derivative of velocity, or you can think of it as the second derivative of position. Okay. So we will take another derivative here, and I'm looking at this velocity function that we found right in here. That was v of t. Okay. So I'm going to use that to take the derivative now for a of t. Okay, because that'll give us a second derivative. And again, we can use power rule on this. So that would be 6t minus 8. Okay, and then derivative of 3 is 0, so that term disappears. All right, so we're good. There's our acceleration function, and so now to find acceleration at the endpoints, we'll plug in our time values. So acceleration at the first endpoint, plug in 0, that would be -8. And our units here are going to be meters per second squared. And in case you don't know where that's coming from, here's where it comes from. Remember that acceleration is a change in velocity over time. So velocity over time. Our units for velocity right now are meters per second, and time is in seconds. So just doing the unit calculation, we have meters per second divided by seconds. And so you could also say that's meters per second times 1/seconds. We're going to end up with meters per second squared for that unit. Okay. So there's our acceleration at our first endpoint. Notice how it is negative. So that could mean either that the object is decelerating or that it's accelerating in the negative direction. So kind of interesting. Okay. And then at our other endpoint, 4, we'll plug that in. 6 times 4 minus 8, that would be 24 minus 8, which would give us 16 meters per second squared. Okay, so there's our accelerations at the endpoints. Then if you wanted to, you could use those to find like an average acceleration or something like that if you needed. But yeah, there's acceleration. And now, part C, when, if ever, during our time interval, does the object change direction? Okay, so this one, part C, changing direction. We got to think about what that means. And here, we're looking at an object moving on a coordinate line. So here's our coordinate line. It's just moving along that. We'll say it's a little little point here representing our object. Now, a coordinate system has a defined positive and negative side to things. So let's say if our object is starting right here, we're going to consider this to be the positive direction and this to be the negative direction. So if we're looking at a change in direction here, we would be seeing where our object is, say, moving this way, and then it's gonna turn around and go back the other way, okay? Now, what happens right here at the turnaround point is that even for just the tiniest of moments, the object has to stop moving forward in that direction, okay? So at some point in there, our velocity is going to be 0. So at the turnaround point, velocity is going to be 0 because it was accelerating in a, or not accelerating, it was moving with velocity in a positive direction. And then it switches to moving with velocity pointed in the negative direction. Okay, so we want to look for a place where velocity switches from positive to negative or from negative to positive. If your object had started out moving this direction, that would be a negative velocity. Negative velocity. And then again, at some point there, if it's going to turn around, it has to stop for a split second to make that transition. So here V is negative. It's going to stop for just a split second, and then it would turn around and go in the positive direction where velocity is positive. Okay, so here velocity would be 0 at that turnaround point. Okay, so let's just kind of summarize that picture here. All right, velocity switches from positive to negative or negative to positive, either way. Okay, at the turnaround point, the velocity is going to be 0 just for a split second there. Okay, so that's what we're going to look for. We're going to look for places where the velocity is 0 and then see at those points if we get a switch in velocity, or if maybe the object was just going in one direction, stopped for a second, and then kept going in that same direction. So that's what we want to look at here. All right, so continuing this, we would want v of t to equal 0, and we already found our velocity function here. There it is. All right, v of t, that's the inside of speed there. This is the first derivative of our position function. So 3t squared minus 8t plus 3. Okay. 3t squared minus 8t plus 3. Okay, now ideally, we would take this and hopefully factor it because we want to set this equal to 0. Okay, to look for those turnaround points. 3t squared minus 8t plus 3 equals 0. The very unfortunate thing about this particular example is that it doesn't factor nicely. Yeah, I tried. It looked like it was going to. I thought it might do something like this, but then it turned out that the signs didn't work for the very last term there. If only that were a minus instead of a plus. So yeah, this doesn't factor, unfortunately. But that's just kind of part of life in calculus here. Sometimes things don't always turn out the way we want them to. They don't always turn out pretty. Not factorable. Okay, but that doesn't mean that we can't solve this. It's just we're going to have to get a little more creative here. And if you can solve it on your calculator, I think that would be okay for this problem. I'll work it through using the quadratic formula for us, but ultimately we'll get some decimal values here. Okay, so solving for t equals negative b plus or minus radical b squared minus 4ac. Oops. Oh, that was a plus. Okay, yeah, I knew something looked weird there. That would have been nice if it was a minus. Wishful thinking. There we go, 4ac all divided by 2a. Okay, so we get 8 plus or minus the square root of 64 minus 36 over 6. And so that'd be 8 plus or minus square root of 28 over 6. And I'll just reduce this down for us in case at some point you had to solve for this in exact form. Oops, getting a little ahead of myself there. In case you had to solve for this in exact form, it's good to know how to do that. So remember to simplify a radical like this. You could look for a perfect square underneath the radical. We have one. It's the 4. So you would get 2 root 7 over 6. And then you can factor and cancel out a 2 from everything. Now remember, when you do this, you literally have to cancel a 2 out of absolutely everything, not just the first term in the numerator. So 2 goes in 4 times, 2 goes in once, 2 goes in 3 times. It's this one that people usually forget about. So we'd have 4 plus or minus the square root of 7 over 3. And so there are 2 solutions here. 4 plus the square root of 7 over 3. 4 plus root 7 over 3. And we'll just look at that as a decimal from here on out. It's about 2.22. And then our other one is 4 minus root 7 over 3. And that is approximately 0.45. And these are in seconds. Okay, phew, all right. So we've got our semi-unfortunate t values. But remember what we're going to use those for. We're going to see if those are true turnaround points, because this is really just a potential turnaround point. And so we need to find out if at those 2 points, if the velocity truly does switch from positive to negative or negative to positive, or if it stays the same sign. Because if it's the same sign, then there was no switch in direction. Okay. So what we're going to do here is we're going to test it out. Okay, so we are testing our velocity function. I'm making a little number line here. Here's our 2 t values, about 0.45 and about 2.22. Okay, I'll put little approximates on those. And we want to test in those different intervals, this interval, the interval in between, and this interval over here, to see what the velocity is doing, to see if it changes or not. So let's check it out. You can pick some test value in each interval. For instance, over here on the far left, I'd probably pick t equals 0 because it's the easiest to plug in. And v of 0, using our v of t function right here. Okay. We would plug in 0, and the first two terms would disappear, and we would just get 3. So that's a positive velocity. All the velocities in this interval are positive. Okay, now move to your next interval here. I might pick t equals 1 in that interval. Just pick something that's easy for you to plug in. And let's check v of 1. That'd be 3 times 1 squared minus 8 times 1 plus 3. And so we'd end up with 6 minus 8, which is -2. So there's a negative velocity. All the velocities in that interval are going to be negative. And last one here. Pick some t value that's bigger than 2.22-ish. And I'll go with t equals 3. V of 3 would be 3 times 3 squared. I'm just going to write 9, keep it quick there. Minus 8 times 3 plus 3. So we would get 27 minus 24 plus 3. And so that'd be positive 6. So all the velocities over there are positive. And so, yeah, we do actually have some changes in direction going on, because our velocity starts out heading in the positive direction. So our little object is going zip, 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 zip in the positive direction. And then at about 0.45 seconds, it stops still for just a split hair of a second there, and then it starts traveling in the negative direction. So it goes zip, 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 zip that way towards the negative. And then it goes in that direction until about 2.22 seconds, when it stops for another split hair of a second there, and then starts traveling back in a positive direction with a positive velocity. So then it keeps going that way for the rest of time. Okay, so that's what our little object is doing. There are 2 switches in direction. So let's make note of that for our solution here. And let's see, how was this worded? When, if ever, during the interval, does the object change direction? Okay, and note that, yes, both of those values are actually in our interval. If one of them had been like 6 seconds or something, that would have fallen outside of the interval. So we have 2 solutions here, though. So changes direction at t equals 4 minus root 7 over 3, approximately 0.45 seconds. And also at t equals 4 plus root 7 over 3, which was about 2.22 seconds. Okay, so there's our answers for that. That one's a bit of a doozy, but hopefully it gets the point across of what we're looking for with changes in direction.